Predicting the oxidation states of elements is a very important thing to know in chemistry. What I've drawn on the screen here is a diagram that only contains the representative elements. Notice the transition metals have been taken out. I've written out the electron configuration of the highest energy electron in each element of that group. For example, in the third group down, we have 3s1, then 3s2, and then if you skip the transition metals, you have 3p1 and 3p2, and so forth. So if you look at the outer electrons, or what we call the valence electrons, in each one of these groups, there's 1 in the first column, 2 in the second column, 3 in that 3p1, because remember that includes the 3s2 and 3p1, and then 4, 5, 6, 7, and 8 electrons in each of their outer shells. So something that has 3p4 has 3s2, 3p4 as its last electron configuration, which means it would have 6 valence electrons. Chemists write out these electrons in dot structures, something called electron dot or Lewis structures. It's a way to show the valence electrons as dots, a quick way to see what they look like. As you notice, the number of valence electrons equals the number of dots. When you write out these electron dot structures, just make sure you have no more than 2 around each side of the element. The X could be replaced by the element symbol. For example, the X in column 1 would be replaced by the element symbol for the 5th period down in the first column, or rubidium. Here's the next 4. Notice once again all the dots are equal to the number of valence electrons. If you notice, the maximum number of dots we can have around an element is 8. That's what makes the noble gases so important in oxidation states. The octet rule states that atoms tend to lose, gain, or share electrons to have the electron configuration of a noble gas, which means that all these elements that are not noble gases would love to gain or lose or share electrons so that they can have 8 dots around their structure. So let's go through an example. In order to fulfill their octet rule, elements will become most stable by the least amount of energy it takes to get its octet rule satisfied. Rubidium, only having 1 valence electron, has 2 choices. It can either gain 7 electrons and have 8 in its outer shell, which would take a lot of energy, or it could lose 1 electron and become 8 that way. And that's the way it would choose, forming rubidium plus 1. Notice that as it loses an electron, it becomes more positive because electrons are negative. So since it has 1 less electron, it now has a positive 1 charge. Of course, as chemists, we wouldn't write that 1. We would write it out as rubidium with just a plus sign. Let's try another one. Gallium has 2 choices. It can either gain 5 electrons and stay in its same row and go all the way to the right and have 8 valence electrons. Or it could lose 1, 2, 3 electrons and look like that noble gas. The way it would choose, I would think, would be to lose 3 electrons instead of gain 5. Losing 3 electrons would take a lot less energy than gaining 5. So that's what it chooses. And we call that gallium 3+. Notice it lost 3 electrons and now has a positive 3 charge. The last example I'm going to do for you is arsenic. Arsenic has 2 choices. Arsenic can either gain 3 electrons or it can lose 5 electrons. Well, gaining 3 electrons takes less energy than losing 5 electrons. So let's see. 1, 2, 3. Arsenic would love to gain 3 electrons, giving it the charge of arsenic 3-. Notice it gained 3 electrons, so its negative charge went up by 3.